So is my screen visible to all of you guys?
Yes, sir.
Okay. So good evening to everyone. Today is the week 11 discussion of this course, Introduction to Machine Learning, and this course is originally taken by Professor Balraman Ravindran, Professor and Head of the Department of Data Science and Artificial Intelligence, IIT Madras, and myself, Ayan Paul. I am a PMRF research scholar from IIT Kharagpur, and my duties is I will first cover some of the important concept that has been taught in the week discussion, and then I will solve some of the question that will help to solve you the assignment problems. Okay, so yeah, someone is joining, I feel. Yeah. Yeah, so let's move on to the discussion. So last week we have entered into this so-called unsupervised learning. Okay, unsupervised learning, we have discussed about clustering. Okay, so clustering we have seen that clustering can be done in two. There are two types of clustering on the basis of clustering. On the basis of type of clusters formed. One is soft clustering, second one is hard clustering. So previously in the previous class, whatever clustering we have discussed, that was hard clustering. What we have discussed, first type, one is density based clustering, one is hierarchical clustering, and one is partitional clustering. Okay, so whatever we have discussed, that was some form of hard clustering. But today we will be discussing something that is a type of soft clustering called Gaussian mixture model. Okay, so before entering into this Gaussian mixture model, what is important is we see what is this so-called uh, Gaussian distribution. Okay, so Gaussian distribution in probability theory, normal distribution or Gaussian distribution is a type of continuous probability distribution for a real valued random variable. Okay, so example of Gaussian distribution, most of the things that we encounter in our real world are some kind of Gaussian distribution. What is the characteristic of Gaussian distribution? If we take the whole population in a Gaussian distribution, your mean population or population that is in between, that will have the maximum amount of population. Okay, and uh, and as we go on decreasing or increasing from mean, that is, if we go left side or right side of the mean, the population of that trait decreases. Okay, so that is Gaussian distribution. For example, let's take this example of height, average height of a let's take an example of height of some of the students in a university. Okay, so you can see that mean distribution, or there will be a certain height which is the average height of all the individual, and the maximum amount of population will have that height. Okay, as we go height greater than this height or lesser than this height, the population keeps on decreasing. Okay, so this is the type of distribution known as Gaussian distribution. You can see in this graph, this type of distribution is known as Gaussian distribution. So average, okay, average or mean, whatever you tell, so average or mean, that constitute the maximum number of population. Okay, if this is a if this y-axis is population or probability of the distribution, you can see the maximum probability will have the mean as the height. Okay, and as we go left side or right side of the mean, the or as we go to a height that is short or taller than this mean, the probability of population decreases. So that is nothing but Gaussian distribution. So this is a curve for Gaussian distribution. This curve is also known as bell-shaped curve. Okay, again I am telling, Gaussian distribution, the curve formed by this Gaussian distribution is known as bell-shaped curve. Okay, so bell shape, you can see the average performance or average height, those who have average height, that will constitute the maximum amount of population, and low performance, that means low height, or high performance, that is high height, as we go on either high height or low height, we have less number of population. So that is how we form our Gaussian distribution. Okay, now you can see this is, yeah, another thing about Gaussian distribution, the middle height is known as mean height. Okay, and there is another term called standard deviation. Okay, standard deviation, what standard deviation determine is the flatness of the curve. Okay, more will be the standard deviation, the more flatter will be the curve, or the more elongated will be the curve. The lesser is the standard deviation, the lesser elongated will be the curve. So this is about Gaussian distribution. Okay, so yeah, this is about Gaussian distribution. Let me pull this. Yeah, this is about Gaussian distribution. Okay, now Gaussian distribution, whatever we are discussing in this example, this is one variable Gaussian distribution, that is we have only one variable, that is height. Okay, so in one dimension or one variable, you can say the probability density function of a Gaussian distribution is given by this formula. Okay, Gx, x is whatever the data, and we have two attributes, two you can say arguments or attributes here, that is one is mean denoted by mu, and the one is sigma, that is standard deviation. Okay, so that will be equal to 1 by sigma root over 2 pi e to the power minus x minus mu whole square divided by 2 sigma square. So that is the probability density function of a Gaussian distribution. Okay, here mu is your mean and sigma is your standard deviation. And what is sigma square? The square of the standard deviation is known as variance. Okay, so that is about one dimension. Okay, someone is joining. Okay. Yeah. So sigma square or the square of the standard deviation is known as variance. Okay, so that is about one dimension. But most of our data that we encounter in our day-to-day life, it is more than one dimension, right? That means it has more than one variable. So for multivariate Gaussian distribution, that is it has more than one variable. Let's say it has d variables. So the probability density function is given by this formula. Here this standard deviation, okay, mu will remain mu, okay, that is mean of that particular mu of that particular dimension. Okay, but standard deviation, there is nothing called standard deviation here. Standard deviation is replaced by something called covariance matrix. Okay, that is sigma. And how we write it? It is almost similar, but some difference is there. That is root over 2 pi. 2 pi. Here we write this covariance. Okay, covariance. Earlier we write this sigma square in the root over, but here we write covariance. Okay, covariance will take care of this sigma square. Okay, that is e to the power, same thing, e to the power x minus mu. Here we are writing it in a matrix form because it cannot be written in a because we have more than one variable, so cannot be written separately. So we are writing this thing in a matrix form. So this mu will be a matrix, okay, of all the mean term. Okay, and this sigma will be a matrix of d cross d covariance matrix. Okay, so same thing, if you will see this x minus mu transpose into x minus mu, that is nothing but x minus mu whole square. Okay, and this sigma is there, so minus half sigma is there, right? So minus half, you can see minus half this sigma to the power minus 1. That means we can bring it down, so that is minus half sigma. So sigma is equivalent to this sigma square. Okay, so capital sigma is equivalent to this small sigma square. Okay, so that is about these are the two formulas of this probability density function of this Gaussian distribution. Okay, so is this clear? Any doubt? Is my voice audible?
Yes, sir.
Okay, so I think it is clear. So why we are studying this Gaussian distribution? Because we have a machine learning model that we will deal next, that is known as Gaussian mixture model. Okay, so Gaussian mixture model. What is this Gaussian mixture model? I have told you previous class whatever we have discussed, that is some kind of hard clustering. Okay, but now today we will discuss a type of soft clustering known as Gaussian mixture model. So what is this Gaussian mixture model? In real life, many data sets can be modeled by Gaussian distribution. Okay, so the Gaussian mixture model intuitively assumes that cluster originate from different Gaussian distribution. Okay, clustering. So we will be forming different clusters. So what this Gaussian mixture model assumes is that the cluster originates from different Gaussian distribution, and we are modeling the dataset as a mixture of this distribution. This forms the core concept of the model. So again I am telling you, clustering, what we do in clustering is we cluster our data, right? So here this Gaussian mixture model assumes that each cluster will be formed from different Gaussian distribution. Okay, so that is the core idea behind this Gaussian mixture model. Okay, so suppose there are k cluster, the probability density function is defined as a linear function of densities of this k distribution. Okay, Gaussian distribution, we just have discussed the formula of probability distribution for each Gaussian. Okay, now here we have a mixture of Gaussian. So whenever we have mixture of Gaussian, this this probability density function is for one Gaussian. Okay, k is the number of clusters, so k equals to 1 to k, capital K. So small k equals to means k equals to 1 to capital K. So we have capital K number of clusters. Okay, so for each cluster we will have a Gaussian distribution separately, but to form the probability distribution of that whole data set, what we will do, we will sum up the Gaussian distribution of each clusters. Okay, and we are multiplying pi k. What is this pi k? Pi k is a mixing coefficient for this kth distribution. Mixing coefficient, okay, the term may be quite complex, but mixing coefficient is nothing but your weight. Okay, you can say it is a weight. Weight means like you have 3 clusters, so you can give a weight of 0.33 to each cluster, right, according to its importance, whatever. So you can give 0.33 weight to each cluster. So this pi k is nothing but that mixing coefficient or the weight that is given to each cluster. So by that we can find the probability density of the whole distribution. Okay, that is that can be taken as weighted sum of each Gaussian distribution of each cluster. Okay, so that is how we write the probability of this Gaussian mixture model. Now about k-means and GMM. K-means, if you will form the what you can say cluster, you can see k-means is a type of hard clustering. Okay, so cluster, if I form the cluster of the k-means here and here, these are not overlapping, that means these are type of hard clustering. Okay, but this GMM, whenever we are finding GMM, as this data is spread, and GMM is a type of soft clustering, so you can see this overlapping cluster. So here also we have 3 clusters, but you can clearly see these clusters are overlapping. So that is the difference between this Gaussian mixture model and or your hard clustering. Okay, now for estimating parameter by maximum log likelihood, compute P probability of X mu sigma pi. Okay, so what we are interested in doing, in calculating the log likelihood of each data point. Okay, so log likelihood of each data point can be find out by this formula, that is ln px. X is your data point, mu sigma and pi is your different attributes. Okay, mu is your mean, sigma is your that covariance matrix, and pi is your mixing coefficient. Okay, so what we are doing, this is nothing but your probability density of that point, and what we are doing, we are summing it from I to n, because what we are doing is we are finding the maximum log likelihood of each data point. So that is why we have n data points, that is why we are adding from I equals to 1 to capital N. Okay, and we have k cluster, capital K cluster, so k equals to 1 to capital K. So by that we are estimating our maximum log likelihood. Now we define a random variable gamma k such that gamma k equals to p k p p probability of cluster, okay, probability of the cluster belonging for that data point. Okay, how we can calculate this? We can calculate this by this formula, that is nothing but Bayes theorem. Okay, if we have if we have px belonging to k, so we can find pk given x. Okay, so how we can find it out? We can find out by this Bayes theorem. So we will write px k into pk divided by all your pk into pxk. Okay, this k, what is k? K is the number of clusters. So first we will find k equals to 1, then k equals to 2, then k equals to 3, like that. By that we can find the gamma k term. Okay, this is also known as some kind of responsibility term. Okay, now here this pk is what? Pk is probability of finding the cluster. What is the probability of finding cluster? That is nothing but your pi k, because pi k is the mixing coefficient. So pi k, pk, we are replacing it by pi k, and we are writing the formula as it is. Okay, so this is this term is known as responsibility term. Okay, so after that now for the log likelihood function to be maximum, what we will do is we will derivate it, we will differentiate it with respect to whatever the term we want. So first we will differentiate it with respect to mu, and whenever we will differentiate it, we will find the mu k. Then we will differentiate it with respect to sigma k. So we will find this, and when we will differentiate it with pi k, we will find this. So that is the whole mathematics behind the Gaussian mixture model. Okay, so is it clear? Am I audible?
Yes, sir. Yes, sir.
Okay.
So this random variable nu k, why we are finding?
Mu k is the mean. Okay, mu k is the mean, means we need to maximize the log likelihood of all the points. Okay, like you remember in the RSS. Okay, that is residual sum of square. What we do? We want to keep the residual sum of square minimum. Okay, for that we find the beta 1, beta naught, beta 1, beta 2, all our parameters, right? So here also what we want our maximum log likelihood to be we want our log likelihood to be maximum. So for finding the maximum, what we have to do? We have to find the parameters. So we have three parameters. One is mu, that is the mean. One is sigma, that is the covariance, and the one is pi. Okay, that is the mixing coefficient. Okay, so we need to find these three parameters. So for finding the three parameter, what we do? We do the differentiation with respect to that term. Okay, so whenever we are doing the differentiation with respect to that term, we will find these three terms. Okay, that is about Gaussian mixture model. Okay.
And the previous one, the gamma k, the random variable, that is gamma, right?
Yeah. Gamma k. Okay, gamma k. So what we know here, we know px given k means we have a cluster, and we will find the probability or probability. Okay, probability of a point given a cluster. But sometimes what we want to do, we want to find the probability of the cluster given the point. So for that we are calculating this gamma k. This gamma k is also known as responsibility term. Okay.
So that is like the complete probability that you were talking about, right? Like the unknown data also is included in that. Is that why we are calculating that?
Yeah, that we will learn unknown data, that we will learn in the next slide. That is about expectation maximization. Okay. Okay. So that is about Gaussian mixture model. Okay. Now we will see the next thing, that is expectation maximization algorithm. Okay, why we want this? The expectation maximum algorithm is an iterative way to find maximum likelihood estimate for the model parameter when data is incomplete. Okay, when the data is incomplete or has some missing data points or has some hidden variables. So EM chooses some random values for the missing data point and estimate a new set of data. These new values are recursively used to estimate a better first date by filling up the missing points until the values get fixed. Okay, so suppose we have a data set, okay, and we have some missing variables. So can we fit our Gaussian mixture model? We cannot fit our Gaussian mixture model. So for that, first we need to estimate our missing data points. Okay, so let's say we have some missing data points, but we randomly chosen some missing data points, but for those missing data point to form a cluster, whether it will form a good cluster or not, that we do not know. That we can know when we are calculating all this three parameter, that is mu, that is mean, sigma that is covariance, and pi k that is your mixing coefficient. Okay, so this expectation maximization algorithm, what it will do, it will randomly choose any data points for your missing data values, and then it iteratively try to find out the maximum likelihood estimate. Okay, and then whenever it will find the maximum likelihood estimate, it will see what are the parameters of the data. Okay, so that is how this expectation maximization work. So it has two steps. Okay, one is E step, that is estimation step, and another one is M step, that is maximization step. So let's see about the E step. So this is the same formula that I have shown in the previous slide. Okay, so E step, what we do in E step or estimation step, in the estimation step we first initialize our model parameter like the mu k, that is mean, covariance matrix that is sigma k, and mixing coefficient that is pi k. Okay, for each data point we calculate the posterior probability. Okay, so yeah, that probability can also be told as posterior probability of data points belonging to each centroid using the current parameter value. This probabilities are often represented by latent variable gamma k. Okay, at the end estimate the value of the latent variable gamma k based on the current. Okay, someone is joining, I think. Yeah, at the end estimate the values of the latent variable gamma k based on the current parameter values. Okay, so first what you will do, estimation step, you will initialize our model parameter like all this. We have three parameters, right? Mean, covariance matrix, and mixing coefficient. So you will initialize some random value for mu k, sigma k, and pi k. Okay, then what you will do, for each data point you will calculate the posterior probability or gamma k. Okay, these probabilities are often represented, yeah, latent variable gamma k. Okay, at the end estimate the value of the latent variable gamma k based on the current parameter values. Okay, so it is an estimation step. So you will just find the probability sample of sample ith belonging to Gaussian kth, that is gamma ik. I is nothing but your data point. So gamma ik means ith point belonging to kth cluster. So kth Gaussian or kth cluster. So that is how we write this gamma ik. Okay, so here I have already explained you, this is the weight, pi k is the weight of the kth Gaussian. This is the probability of ith sample, means ith data point was generated by kth Gaussian. Okay, and this is nothing but weighted sum over the probabilities that the sample ith was generated by jth Gaussian. So same thing, nothing to explain here. Now let's see the maximization step. Now we have this maximization step. So in the maximization step we update the values. Okay, we update the values mu k, sigma k, and pi k using this estimated latent variable. Okay, so here are the formula for by using this gamma ik, what we do, we will find the new, okay, we will find the we update this parameters. Okay, because in the estimation step what we have randomly chosen this parameter. In this maximization step our idea is to update these parameters. Okay, so we will update the mean of the cluster mu k by taking the weighted average of the data point using the corresponding latent variable probability. So by this formula what we will do, we will maximize this mu k. Now we will update the covariance matrix, okay, sigma k, by taking the weighted average of the squared differences between the data points and the mean, that is xi minus mu k square, using the corresponding latent variable probabilities. Okay, and we will be updating this pi k. Okay, pi k we will update this by taking the average of latent variable probabilities of each component. Okay, so that is how in maximization step you update it. So there are two steps. Okay, very in a simple sense there are two steps. One is estimation step, second one is this maximization step. Estimation step, what you do, you just randomly choose and initialize our model parameters mu k, sigma k and pi k. You calculate these latent variables, and then in maximization step you update these parameters, that is pi k, mu k and sigma k, by this formulas. And how this algorithm work, we have to repeat this E step and M step until convergence. So we iterate between this estimation step and maximization step until the change in log likelihood or the parameters falls below a predefined threshold. So we have a certain kind of threshold. So we will keep on iterating this process, each step and M step we will repeat. Iterate means nothing but repetition again and again. So we will iterate between this estimation step and maximization step until the changes in the log likelihood or the parameter falls below a predefined threshold. So we will have some threshold. If our log likelihood will fall below a predefined threshold or until a maximum number of iteration is reached, we will keep on iterating this process. Basically, estimation step, we update the latent variable based on current parameter value. In the maximization step, we update the parameter value using the estimated latent variables. Okay, this process is iteratively repeated until our model converges. So this is the whole thing about our estimation maximization algorithm. Okay, so is this clear? So we have two steps, one is estimation step and the one is maximization step. Estimation step, we will initialize our parameter, okay, and then we will find the latent variable, and in maximization step we will update the parameter that we have estimated in our estimation step, and we will keep on repeating until our maximum log likelihood is reached or until the maximum number of iteration is completed. Okay, so that is nothing but our estimation maximization algorithm. Okay, so is this clear?
Yes.
Okay.
Yes, sir.
Okay, so yeah, so before going into the next thing, okay, I want to discuss a numerical problem, but this time we will solve a numerical problem with help of coding. Okay, so let me show you this. So let me stop presenting this. So is the slide visible to all of you? Slide or whatever, code visible to all of you?
Yes, sir. Yes.
Okay. So we have a Gaussian mixture. What we will do, we will solve some of the numerical based on the Gaussian mixture model. Okay, but this time what we will do by coding, because manually it is difficult. So we have inbuilt libraries. We will use this and we will solve our question easily. Okay, so what is this thing? This is known as Google Collaboratory. Okay, so people might know this or might not know this, or some of you are very new to this coding. This is nothing but IDE provided by Google. What is IDE? You can say there is a language, okay, but to write that language we need a notebook, right? And we need a notebook or something. So this notebook or something is nothing but your IDE. Okay, that is integrated development environment. Okay, now we will do coding. So coding is a language. Okay, this is a Python coding we will do. So coding is a language, but to write that language we need a copy. Okay, so copy, we are using this Google Collaboratory. Why we are using this Google Collaboratory? There are other IDs like VS Code you can use, Anaconda you can use, but the problem with all these are that are local IDs. That means we have to install that app first, and then we have to install that application first, and then we can do the coding there. And second problem of there is whatever the libraries we are installing. Okay, for example, for first time I am installing some libraries. Okay, second time again when I will install the new libraries, it will replace the last libraries if we are operating in a local environment. Okay, otherwise we can create a virtual environment and again run our code in that environment, but it is a time taking process. Second important point about Google Collaboratory is that it provides us additional GPUs. Okay, means your computer might have limited the resources, like GPU, you might not have GPU in your computer. So if don't have GPU, or your CPU is not that strong, your code will take much time to execute. Okay, so to avoid this problem, we will do all our work in Google Collaboratory. So Google Collaboratory give you additional GPUs and TPUs. If I get into the runtime, you can see it gives us additional GPU and TPU. Okay, so that is the advantage of Google Collaboratory. Okay, this is basically a simple code, so we can easily do this without any GPU. Okay, so here we have 3 questions to solve. So first question is for question 1 to 3, use the following data, constitute 8 points xi yi. So xi yi we have 8 points, that is xi comma yi 1 comma 1.5, then 1.8 comma 1.2, 0.9 comma 1.6, 8.2 comma 7.3, 9.1 comma 7.2, 7.8 comma 9.5, 7.6 comma 8, and 8.8 comma 7.5. The question is we have to fit a GMM with 2 components for this data. Component is nothing but number of clusters. 2 component means we will fit our GMM with 2 clusters. Okay, what are the mixing coefficient of the learned component, that we have to find out. Okay, this is the question. We have to find out the mixing coefficient of the learned component. Okay, we have to use a sklearn implementation. Sklearn is a popular machine learning library that Python use. Sklearn is scikit-learn. So all your most of the machine learning model will have module in this library. Okay, library, you know, library, it has all kind of books. Similarly, in a Python library, it has all kind of modules. Okay, so sklearn is a library that is popularly used for machine learning. It has all kind of your modules. Okay, so use the sklearn implementation of GMM with random state equals to 0. Do not change the default parameters. Okay, we have a second question. So using the model trained in question number 1, we have to compute the log likelihood of the following points. Okay, so which of the points has the highest log likelihood of being sampled from the model, that we will see. Okay, 4 points are given, so we have to see, we have to check which of the points has the maximum log likelihood. Now third, let model A of the GMM with 2 components that was trained in question 1 using the same data from question 1 estimate a GMM with 3 component model P. Means in first question whatever we have created a Gaussian mixture model with 2 components or 2 cluster. Now in the third question it has been asked that we have to estimate this GMM for 3 components. Okay, note, use the sklearn implementation of GMM with random state equals to 0 and other default parameter. Okay, what is this random state equals to 0? Random state equals to 0 means it will take the data that has been specified to it. If we will change the random state for something like 42 or anything, so after the 42 iteration it will again for each iteration it will be taking different data, that we do not want. Okay, we want to seed our random state. That is why we have kept our random state 0. That means whenever we will run the code, each time we run the code, we will get the same answer. Okay, so that is why random state equals to 0. If we let's say give random state equals to 42, so after 42 iteration only we will get the same answer. Okay, so that is about random state. And all other default parameters, select pairs of points that have the same label in model A but different label in model B. Label means nothing but the cluster. Means whenever we have made 2 components or 2 cluster, so your data points, your 8 data points will be in 2 cluster. That is, if I say your 2 cluster will be one labeled as 0 and the labeled as 1. Some of your data points will be in 0 labeled cluster, some of your data point will be 1 label cluster. But whenever you are making GMM with 3 components, so you have to give 3 labels, that is 0, 1 and 2. So we have to check whether these points belong to the same level or different level. Okay, so that is our 3 questions. So any doubt in the questions? Any doubt in the questions? Is my voice audible?
Yes, sir.
Okay, so no doubt in the questions, right? We have 3 questions with us.
No, sir.
Okay, so we will be proceeding to the coding part. Okay, yeah. So first thing is first thing is, let's see, we have to connect it. Okay, so it might take time. Let's see. I hope it gets connected.
Sir, this type of questions will get in the exams, sir, main exam, or just only for our understanding?
It's difficult. I think it will not come in the main exam, but I think you should learn this coding.
No,
That
because,
is yeah. It
yes,
is difficult. I
because
think
it's a Python
yeah,
program
yeah,
and
yeah,
run and
yeah.
yes, sir.
So we
Yes, okay, sir.
yeah. So in the first step we have connected our Google Collaboratory. Okay, then we will run the code step by step. So first thing is importing the necessary libraries. So what libraries we will install? First we will install NumPy. NumPy is a library that takes all the care of all your numerical operation, like to find the mean. Okay, first to form an array of whatever the data point, then let's say find the mean. What is the if we give some of the random points, so what is the maximum value out of this random point? All the mathematical operation are done by this NumPy library. Okay, so we are importing this NumPy as NP. Now we will import matplotlib.pyplot as PLT. So matplotlib is again a popular Python library.
The
It will
button is not visible, sir.
okay, it is not visible. Is it
No,
visible?
sir, no, sir, just only audio. Yeah, now it's visible.
Visible, right?
Yes, sir, it's visible.
Yeah.
Yeah.
So NumPy, then matplotlib is used for plotting the graphs. Okay, so whatever the model we have, we want to visualize those models. So that for that we use this matplotlib. Matplotlib is used for plotting all our data points, plotting or forming some type of graphs. So for that we use this matplotlib. Then we have this sklearn, that is scikit-learn, that is a popular library for machine learning, and from this library we are importing our model Gaussian mixture. Okay, and then last we are again using this matplotlib library to form. Okay, someone is joining the meeting. Yeah, and then from this matplotlib we are importing this ellipse. Why we are importing this ellipse? Because we need to, for plotting this Gaussian mixture, we need to form the ellipse or to visualize the cluster. So that is why we are importing this ellipse. Okay, now we will run it. Okay, let's see, it will run. Okay, so it has been run. Okay, so our first thing has been run, that is importing the necessary libraries. We are done with importing the necessary libraries. Now we have this data point, so we have to run this command. So we will yeah, I have told you we have to write the data point with the help of NumPy library, because NumPy takes account with all the data points, etc., all the data points and all the mathematical operations. Okay, so that is why I am assigning a variable x, and this x will have all your data points. Okay, so we will again run this. So our data points has been assigned to this variable x. Now function to plot GMM result with confidence ellipsis. To form this ellipsis, okay, so what we are doing is we are just assigning a function. Okay, so this function, it has been written like this. So this portion is only important for you to remember, that is plot GMM will be the model that we will assign in the next step. X is just I have shown you, x is the variable for all the data points that we have assigned. And label means whatever the cluster we are forming, we want to give it a label, right? For example, first cluster it will be 0 level, second cluster it will be 1 level, third cluster it will be 2 level, like that. So this label. So again we will run this. What we are doing this? We are doing this to function. We are running this code as this is a function to plot GMM result with confidence ellipsis. Now we will again run a function to draw ellipsis for covariance. Okay. Now covariance will determine the spread of your data points. So again we have to assume a function. So this function takes the function takes this all arguments, and again we will run this code. Okay, so this you need to remember, and then our main thing start with this step. Okay, we have to fit GMM with 2 component. Why we are fitting this GMM with 2 component? Because it has been told in our question, first question, fit a GMM with 2 component for this that. So that is why we are fitting the GMM with 2 components. So let's see. Okay, so in this step we are fitting the GMM with 2 components. So that is how we are writing this GMM2, that means 2 components. That is why I have assigned the variable GMM2. You can assign anything, like you can assign GMMX or GMMY, anything you can assign. This is just a variable, so anything you can assign. Okay, you can also assign the name, any variable you can assign. So this GMM2 is nothing but it is a Gaussian mixture. It will have n component equals to 2 because we are fitting the GMM with 2 components. Random state equals to 0. Why random state equals to 0? Because we do not want our answer to change again and again. Okay, so that is why we are seeding the random variable. So that is why, okay, someone is joining. Yeah, so that is why random state equals to 0 and dot fit x, because we have to fit at the GMM with our data set. That is why our data set is x, so that is why we are fitting the x. So we are let's run this. Okay, so we have run this, and we have fit our data set x with this GMM Gaussian mixture that has 2 components and random state equals to 0. Now next step is to display parameter of the GMM. Okay, so for that we will print the parameters. Okay, now what are the parameters that we will print? First we will print the mean. Okay, how we will calculate the mean? We do not like whatever the formula we have discussed in the class. Nothing we have to apply. We have a library called Gaussian mixture, module called Gaussian mixture. We have assigned that module with our variable GMM2, and just we have to call the mean function, that is GMM2.means. Okay, now again for finding the covariances, nothing we have to we need not to do the long calculation. We will say GMM2.covariances, and again for mixing coefficient we will do GMM2.weights. Okay, we will run this and you will find the results. Okay. So this is the mean that has come. As we have 2 clusters, so that is why we have 4 values. Why we have 4 values? Because each cluster will have 2 attributes, right? X as well as Y. So that is why first cluster form that has mean 8.3, 7.9. second cluster form that has mean 1.2233 and 1.2233 comma 1.4333. Okay, so these are the means we have got. Now covariances we have got this covariances as we have 2 cross 2 thing, because we have covariances, it's between the clusters. Okay, so covariances we have d cross d, that means 2 cross 2 data 2 cross 2 2 cross 2 attributes. So that is why covariances, these are the covariances form. Okay, that we have find out just by a line of code. Nothing we have to do calculation or nothing, but we will just find out by this code. But our question was find the what are the mixing coefficient for the learned component. So mixing coefficient I have told you that will be find out by GMM2, that is our variable that we have assigned for the Gaussian mixture model with 2 components dot weights. Okay, that we will do, and we will find the coefficient, mixing coefficient. So first cluster or W1 will be equal to W1 or pi 1 will be equal to 0.625 and pi 2 will be equal to 0.375. So this is the answer of the first question that has been asked. So again I am showing you the first question: fit a GMM with 2 components for this data. What are the mixing coefficient? That has been asked in the question, right? What are the mixing coefficient of the learned components? So we have just found the mixing coefficient, that is 0.625, 0.375. That is pi 1 equals to 0.625 and pi 2 will be 0.375. Okay, is this clear? First question how we have solved? We have solved by literally 2-3 line of code, right? This whenever we have print out all this, that is GMM2 dot means, GMM2 dot covariances and GMM2 dot weights, we have found out the required results. Okay, is the first question clear to all of you?
So the code GMM was part of the library, or this
GMM2 is the variable. Gaussian mixture is a module of the library scikit-learn. Okay, this is the Gaussian mixture. This is a module from your library scikit-learn. So first we have installed that library, then we have imported this Gaussian mixture from that library, and then we have assigned a variable. That variable, what that variable will do, you can assign anything like GMM5, GMM10, anything you guess. Okay, this is nothing but GMM2. Anything you can assign, like your name also you can assign. Okay, that will be equal to Gaussian mixture n equals to 2, because we have to fit this GMM with 2 components, that is 2 clusters, and random state equals to 0, because we do not want our answer to change again and again. We have a fixed data set, so that is why random state equals to 0. And dot fit x means we are fitting our data set to this model. So by that, this our model got created by this name GMM2. Okay, and then we have to just GMM2 dot means, GMM2 dot covariance and GMM2 dot weight to find out all these parameters. We have 3 parameters, mean, covariance, and last thing is mixing coefficient. So to find out the 3 parameters, we will just write this 3 things. Okay, GMM2 dot means, yeah, please.
That for k nearest neighbors also you are only specifying k, right? Here also you are only specifying the number of clusters.
Yeah. It has been told in the question only that we have to take 2 clusters, so that is why we are specifying it as 2. Okay.
Okay, but what is the general difference? The covariance, I think it will be fixed or something. Or?
Can you please repeat?
No, in general, what is the difference between, you said soft clustering, right? So
yeah, what is the difference you are asking between GMM and this k means, right?
K nearest neighbor.
K nearest neighbor means k means clustering. Okay, k means clustering. The difference between k means clustering and GMM is that GMM assumes that every cluster will be formed from a Gaussian distribution, but k means it is not so. Okay, so that is the main difference. So that is why we have means and covariance for this for a particular cluster, like the 2 clusters are formed, right? So these are the mean for this first cluster, this is the mean for the second cluster. Similarly, covariance, as we have two variable, that is xi and yi. For first cluster we have this, and for second cluster we have this covariance. Okay, so that is the difference. And also we have mixing coefficient here, because it is a type of soft clustering, so we are giving some weight to first cluster as well as some weight to second cluster, so that is why mixing coefficient. Okay. If we compare with k-means, so it has only means for each cluster. It first of all, it does not necessarily assume that each distribution is a Gaussian, each cluster is a Gaussian distribution. Second, it will only calculate the mean of each cluster, nothing called covariance. And third, we also don't have weights for each cluster. Okay, so these are some of the difference you can draw out. Okay. Okay, so we are done with the first question. What is the second question? Second question is, using the model trained in question 1, compute the log likelihood of the following point. Which of these points has the highest log likelihood of being sampled from the model? So we have 4 points. We have to see we have to find out the log likelihood of each point and see which point has the maximum log likelihood. So we will first, how we will, okay. So before that, what we will do, before that, responsibility is also, you can again compute the responsibility. Okay, responsibility is nothing but this gamma k. So responsibility for 8 points, you can because you have 8 points, 2 clusters, so each point you have 2 responsibility, one for one cluster and other for another cluster. Okay, so one means the point belong to that cluster. Okay, and this one means the point belongs to that cluster. So if I check for this one means the first point will be belonging to the second cluster, and here you can see the first point also belong to the first cluster, as it is kind of soft clustering, but its probability is very less, e to the power minus 130. That is very less, but here it is 1. So your point will belong to this cluster, but as it is a soft clustering problem, so we are assuming some kind of probability in first cluster also. That is very small, but there is some probability. Okay, so that is the thing. So responsibility also you can calculate. For each point you can calculate the responsibility. How you can calculate? You can calculate by this hello.
Sir, one doubt, sir.
Yeah, please.
This predict underscore proba is a function which is there in the library of Gaussian mixture. The predict underscore proba.
Yeah. It is in the module. Okay, it is in the module.
Okay.
It is a function that is in the module of the Gaussian mixture.
Module, that is, okay, Gaussian distribution module. Okay.
Yeah, Gaussian
This
mixture
is a
model.
keyword. Is it predict underscore proba is a keyword
Function.
for the
You can say it as a function. Okay. First,
Oh.
this is your module, Gaussian mixture. Okay, this is your library, scalar. This is your library.
Oh.
This is your module. In this module, what we have we have assigned a variable to fit the model. Okay, this is our variable that we have assigned to fit the Gaussian mixture model. This is GMM2. Okay, so once we have
Okay.
then what we have done, then we have called the function. Okay, GMM2 predict.prob x. Okay, and that we have called it as another variable called responsibility, that you can call, or simply you can write this in here. Okay, that will also solve your thing. But for simplicity, what I have done is I have again called a variable. I have again assigned a variable for this. Okay, for this responsibility. So by this you can
Can you come bit up, sir? I want to see the points which how we had assigned the question points. Can you please come bit up? The first thing.
here.
Yeah, this x is equal to np dot array. This data points.
You have this data points, right? 1, 1.5. You have 8 data points. 1, 1.5, 1.8, 1.2, like this, right? 8 data points you have, right?
This np is number of Python. Oh, number type in Python as np is it? Okay.
NumPy library. Okay, This NumPy is a library that takes care of all your mathematical operation. Okay.
Okay. Thanks, sir. Thanks.
Okay, so whatever, yeah. So responsibility also, we have got the responsibility. You can run the code. I am not running. I have already run. Okay, let's run. Let's see. Let's run. Okay, it might take some time, so that is why. Yeah, it has run. So these are the these are the responsibility of all the point that we have got. As we have two clusters, so that is why two responsibility for each point. Okay. Now, and the thing is to visualize the GMM model. So to visualize this, we have this function plot GMM. Okay, plot GMM. This is the function plot GMM, and this is our model GMM2. X is the data point, and label equals to two component, because we need two component. So whenever we have done this, we have got our is this visible to all of you? Is this chart? Can I make it small? Yeah, this is the Gaussian distribution. Okay, we have 8 points, so 3 points is covered by this cluster and 5 points is covered by this cluster. Okay, any doubt regarding this? We are just visualizing the model. Whatever model we have created, we are just
5 points is the bigger elite.
Yeah,
5 points are the bigger elites, is it? 3 points are
yeah. These are the 3 points. Okay, this blue dots you can see, these are the 3 points. This blue dot you can see, these are the 5 points. So this is one cluster, this is another cluster. Okay, so let's label it as 0 and let's label it as 1. So 0 we have 3 points, and for 1 level we have 5 points. Okay, so we are just visualizing this by this code. Okay, let's make it a big. Okay, let's make it a big. Okay. This is right, I think. Okay, so we will just plot it by this plot GMM, that is the function that we are taking from that library. Okay, and GMM2, because this is our model, X is this is our data, and it will take 3 arguments. First it will take models, that is GMM2, then it will take dataset, that is X, and then it will ask the components. So we are assigning it for 2 components, so that is why label equals to 2 components. Okay, so by this we can visualize our model. Now next thing, as we have been asked in the next question, to given the data points, we have this 1 2 3 4 data points, we have to find the maximum log likelihood. Okay, so these are the points. Again, we are assigning these points in the form of array. Okay, we are putting a variable called points. Okay, and we are assigning it in the form of the numpy array, np.array, and we have 1 2 3 4 points that has been asked in the question. So 4 points I have assigned. Now there is a thing for log likelihood. Okay, so log likelihood, we are assigning a variable called log likelihood, and how we will find out the log likelihood of that points, that is GMM2, that is nothing but your model dot score samples points. This you have to remember, score sample points. Okay, so by that you are finding log likelihood for each points, because points are, these are the points we have assigned. So this points is nothing but your argument of the data points that you have assigned. So that is why points I have written. If you are assigning here x or y, you have to put x or y here. Whatever you are doing, whatever you are assigning the variable for the points, so here you have to put that. And then I am just printing the log likelihood. Okay, and your log likelihood will be there. So for point first, that is 2 comma 0.5, this is your log likelihood. Okay, for point minus 1 comma minus 0.5, this is your log likelihood. For 7.5 comma 8.0, okay, this is your log likelihood, and 0.5.0 comma 5.5, this is your log likelihood. So what we have to do, we have to identify the point with maximum log likelihood, right? So for that, this is your code, point np.argmax. So maximum, how we can find the maximum out of this 4? How we can find out the maximum? We can find out the maximum by this function, that is np.argmax log likelihood. Okay, so np.argmax and log likelihood was our variable. So by that we are finding the maximum point with highest log likelihood, and we have assigned this highest log likelihood by this variable highest log likelihood point, and that is coming 7.5 comma 8.0. okay, because you can see here this is minus 278, minus 493, minus 2 and minus 55. So out of this, which point has the maximum log likelihood? That is minus 2, and that is 7.5, 8.0. So your point with maximum highest log likelihood is 7.5, 8.0. So this is the answer. Okay, so we are also done with the second answer. Okay, second question answer. So is it clear to all of you?
The GMM2 dot samples, that was returning log likelihood, is it?
Yeah, GMM2 dot scores underscore samples.
Score.
Yeah, this is the function for finding the log likelihood. Okay.
Okay, but is it given in some documentation? Okay.
Yeah, you can scroll over here and you will find this. Also, you can go to scikit-learn. Okay, sklearn is a library, so you can type sklearn, then Gaussian mixture model, and you will have a documentation there. You can find all the formulas, whatever you all the codes, whatever you want. Okay, or otherwise you can scroll here, and as the internet, I think it is a bit slow, so it will be loading some of your thing. Okay, clear?
Yeah.
Okay, so we are done with the first question. We are done with the second question. Now we have to solve the third question. What the third question is asking? Third question is asking, let the model A, okay, let model A be the GMM with two components that was trained in question number 1. Okay, that was the model A. Now using the same data in question 1, estimate a GMM with 3 component model B. So using the same data, we have to create another model GMM, another model called model B, and now this GMM will have 3 components or 3 clusters. Okay. Note, use the sklearn and all this. Select the points that have the same label in model A but different label in model B. So same label in model A but different label in model B. That point we have to detect out of all this pairs of point. Okay. So let's see how we will solve this. So you understood the question, right? Whatever we have to do, we have to again make a second model called model B. And this model B will have 3 components. Earlier we have 2 components. Now this model will have 3 components. And someone, how we will solve this in exam? Exam, I think this question will not come in exam. Okay, this coding question will not come in exam. But as you are learning this machine learning, so you also need to have a knowledge of the codes. Okay, so for that I am explaining you. Okay, Yuva Lakshmi, is it clear? Okay, so third question, now we have to fit our model with 3 components, that is 3 clusters. So now we are assigning a different variable called GMM3, and that will be Gaussian mixture, and component equals to 3 because now the number of cluster will be 3, and random state equals to 0 because we do not want our answer to change again and again, and we are fitting our this Gaussian mixture model with the same data set. So that is why fit X. Okay, same thing. Earlier we have done it, GMM2 Gaussian mixture and component equals to 2, random state 0, fit X. That we have done for GMM2. Now we are creating another model, that is model B. So GMM3 I have assigned a name. Any name you can assign. You can either assign your name or any name you can assign. Okay, and then you will call this. Okay, you will write this code and you will fit the model. So now I have fit another model, and now again I am displaying the parameters of this 3 component GMM. As now this is a 3 component GMM, now it will have 3 cluster. So mean, it will have 3 means for 3 different cluster. That is why 3 means. So that is why first mean is 8.7, 7.333. This is the second mean, and this is the third mean. But covariance also, we will have 3 different covariance. Each covariance will have 2 cross 2 component, as xi yi is there. So that is why xi yi is there. That means two variables are there. So that is why each covariance of each cluster will have 4 components. Okay, and out of this 4 components also there will be a single common component. Okay, so that is how, as we have 3 clusters, so 3 different covariance, and we will have four parameters for each covariance. Okay, now mixing coefficient, as we have 3 clusters, so that is why 3 mixing coefficient. So earlier it was 6.75, 0.675 and 0.25, like that, 0.675 and 0.25, something like that, right? Earlier we have 0.625 and 0.375, and now we have this mixing coefficient as 0.375, 0.375 and 0.25. This is pi 1, this is pi 2, this is pi 3. Okay, so we have 3 mixing coefficient. Now we visualize the 3 component GMM. Yeah, now we again visualize here. This components will remain the same. Okay, this component or this cluster remain the same, but this cluster is broken into 2 clusters, one of 2 data points and another one of 3 data points. Okay, so by that we are creating 3 different clusters. Okay, again the same thing. Now our model is GMM3, so that is why GMM3. Earlier it was GMM2, so now it was GMM3, and this is the X data you have to set, and this is the label, that is 3 components. Okay, so this is what we have got. Okay, we have got our next GMM with 3 components. Okay, now what our target is? Our target is to find the labels of the point. So labeled to find the label of the first point, we have assigned this label to equals to gmm2.predictx. Okay, and we are assigning another variable called label3, that is for third model B. This is for model, yeah, let me write it. Okay, this is for model, this is for model A, and this is for model B. Okay, okay, so yeah, this is for model A, to get the label of model A. Okay, yeah, to get the label of each data point for each data point belonging to cluster of model A, we are assigning this variable label to gmm2.predictx. X is your data point, each data point, and we are predicting it will belong to which cluster, that is it will take which labels. Okay, and then gmm3.predictx. So this we are assigning this variable for our next model, that is model B, with 3 components or 3 clusters. So gmm3.predictx. Now we will print the labels. Now you can see the labels from GMM with 2 components, 1 1 1 0 0 0 0. So 0 1 are the name of the cluster. As I have shown you in the first, yeah, as I have shown you here in the GMM with 2 cluster, we have one cluster with 5 points and the cluster with 3 points. So this cluster has been assigned, I think, 1, and this cluster has been assigned 0. So 0, we have 3 points with 0, and we have 5 points with 1. So that is what has been written, that we have got from code. Okay, so yeah, 1 has been assigned with 3 points, so 1 1 1, and 0 has been assigned for the other 5 points, that is 0 0 0 0 0. Okay, we have 8 points. Now in the second model or model B, label for GMM with 3 components, we have 3 data points with 1, we have 2 data points with 0, and we have we have 3 data points with 0, and we have 2 data points with 2. Okay, so that is how we have labeled our points. Okay, how the points are labeled according to the cluster of each model. Okay, now what we have to do, according to the question, we have to check whether this belongs to the same cluster or different cluster. Okay, in both the model. So first has been asked this. Why we have written this? Because it has been asked in our question, right? This is what has been asked, that option A 1.0, 1.5 and 0.9, 1.6, whether they belong to the same cluster in model A and different cluster in model B, that we have to determine. So that is how we have written the last code. Okay, so where I have written, yeah, so this is the option A, 1.0, 1.5 and 0.9 and 1.6. 0, 2 is nothing but position of that points. Okay, so 0 comma 2 means position of 1.0 1.5. We have 8 points, right? We have 8 points, so first point is assigned 0, second point is assigned 1, third point assigned 2, like that. Each point is numbered like that. So 1.0 comma 1.5 means the first point will be assigned 0, and this is our third point, so that is why 0 comma 2. And here this is our second point, and this is our third point. Here this is our 6th point, and this is our 8th point. Here this is our 6th point, and this is our 7th point. Here this is our 4th point, and this is our 7th point. Okay, that is why I have written this. And then we have to see a pair that has same level in model A or different level in model B. So already label has been given to all the points. So accordingly this code will detect whether this pair 7.8 comma 9.5 and 8.8 comma 7.5, that is this code, this thing. Okay, your 6th point and the 7th point. Okay, so this has same level in model A. It will have same level in model A, but it has different level in model B. Now again this one, okay, 8.2 comma 7.3 and 7.6 comma 8.0 has same level in model A but different level in model B. Okay, so by this C and D is our correct answer. Okay, C and D. Yeah. Let me go to the question. This 7.8 comma what was the answer coming? 7.8, 8.8, 8.2, 7.6. Okay, so let's check which answer. 7.8, 7.6, 8.2. So yeah, D and E is your correct answer. Okay, it has same level in model A but has different label in model B. Okay, D and E is your correct answer. So is this clear to all of you?
Sir, in the past data type, we are giving this 1.0, 1.5 and 0.9, 1.6 as in the question, right?
Yeah. This is your option A, this is your option B, option C, option D and option E. Yeah, please repeat.
Can you please explain what is the 0, 2 and 1, 2, 5, 7?
0, 2 is positioning of the number, right? Like, yeah, let me show where we have assigned the data in the second step, right? Yeah, this is your 0, 1.0, 1.5, this is your 0, 1.8, 1.2, this is 1, 0.9, 1.6, this is 2, 8.2, 7.3, this is 3, 9.1, 7. Like this. Okay,
this is the pairs number for starting with the 0.
Yeah,
coordinates number starting with the 0, right?
Yeah. In this computer language, we always start our number, sequence with 0. Okay. So that is the code for this. Is it clear to all of you?
Actually, this Gaussian mixture models is for the missing data points, right? This is what we are using.
Gaussian mixture model does not take in for missing data point. Expectation maximization takes account for missing data points.
Okay.
So that output can you show again for model A, model B?
This labels you are telling? This is
Yeah,
let's say
label.
this is 0. Okay, where is my key? This is your 0, this is your first point.
0, 1 and
Yeah, this is your first point, this is your 2 point, this is your third point. Similarly, this is your 7 point. Okay, these are 7 different points. Now we are assuming as in the first GMM with 2 component, we have 2 clusters. So one cluster is 0 and the cluster is 1. So for 0 cluster, these are the points with 0 cluster, these are the points with first cluster. Okay, in this 3 component GMM, we have this 3 cluster, right? So one cluster we are assuming 0, and the cluster we are assuming 1, and the cluster we are assuming 2. So this first 3 point will be going to first cluster. This one cluster with label 1. This 2 points will go to go to cluster with label 0, this 2 point will go to cluster with label 2, and this last point will go to cluster with label 0. Okay.
Okay. Yeah, and that pairwise thing, can you say that again?
Yeah, pairwise I have just written the according, we have 5 options, right? A, B, C, D, E, right? So I have just written A, B, C, D and E option. Okay, and this is nothing but your position of the point. 1.0 comma 1.5 is at the 0 at position, 0.9 1.6 is at the third position, so that is why 0 comma 2. Okay.
So what is that 0, 2? That I didn't get.
0 comma 2, right? Let me again explain. Okay, so this is 1.0 comma 1.5. okay, this is 0.9 comma 1.6. you just remember this 2 point, and let me show you. This is your data, right? So the first point is assumed 0, that is why it was 1.0 comma 1.5, so that is why 0, and next point was 0.9 comma 1.6. so this is your 1 point, this is your second, this is your third, this is your 4, 5th, 6th, 7th. so this is your 0, that is why 0, and this is your 2, that is why 2. Okay, 0, 1, 2, 3, 4, 5, 6, 7. Okay, first option was 1.0 comma 1.5 and 0.9 comma 1.6. so 1.0 comma 1.5 is 0 and 0.9 comma 1.6 is 2. Okay, clear?
Sorry, it's not loading for me. I'm not able to see that properly.
Sir, actually we are not able to see the coordinates, sir. It is in the pairs screen, sir.
You are not able to see? You are able to see, right?
We are not able to see the coordinate screen. Only pairs screen still we are there. We are still in the pairs screen.
Now it is visible, right? Data point xi, yi, x equals to np dot array. It is visible, right? Or not?
No, sir. We are in the last step, right? The pairs is equal to open parenthesis 1.0, 1.5 and 0.9 comma 1.6 is equal to 0 comma 2. We are in that screen only still, sir.
Still you are in that only?
You are coordinate.
Okay, let me stop.
Yes,
let me stop and let me again present. There might be some issue.
But maybe your video, if you stop, a little bit more bandwidth can be there.
Yeah, so let me stop my video. Is the thing shared?
Not yet.
Not yet, sir. Now it is getting loaded.
Yes.
Yes, sir.
Now it is loaded, right?
Yeah, now we are on the data points xy.
Yeah. So data point comma xi yy. Your doubt was 1.0 comma 1.5 and 0.9 comma 1.6. How it is assigned 0 2, right? That is your doubt, right?
Correct.
Yeah. So in this array you can see this first point is 0, second point is 1, third point is 2, fourth point is 3, 4, 5th, 6th and 7th. Okay, clear? 0?
Those are the indexes in the NumPy array.
Yeah. These are nothing but indexes in your NumPy array. Okay? So is it clear to all of you?
Okay.
All the 3 questions?
Why we have taken only that pairs, something like 0, 2, 5, 7. Why cannot be 0 and 1, 0 and 2, 0 and 3 or something like this?
That is how you have to code this, right? This is called dict, okay? Dictionary. Okay, dictionary, this is your key and this is your value. Okay, so you have to learn more thing about coding, then you can
No.
Understand? Okay.
Okay.
Okay. So by this I am terminating this code, and now we will be discussing about discussing some of the question. Okay. So yeah, before that I want to show another thing. Okay. Yeah, before that I want to show this. Sorry, I want to what? Yeah, I want to share this. Okay. Is this thing shared to all of you? Is the screen visible?
Yes. Yes.
Yeah, this is nothing but whenever you will
Yes, sir.
open your SWAYAM portal, below that there will be a thing called problem solving session. Okay, whenever you will open that, you will be directed to a page. In that page, in the second column, you will see my name, Ayan Paul. Okay, you will first see a YouTube video. After that, you will see a folder. Okay, this is the same folder. Okay, in this folder, what I have done is I have kept some of the codes, because it is not easy to discuss code with you, because it will take much time. But whatever the models that we have discussed so far, what I have done is I have what I have done is yeah what I have yeah what I have done is I have given you this folder. Okay, whenever you will open this folder, you will have all the codes for all the models that has been discussed. Okay, so you can go through the codes and you can have more understanding about the codes. Okay, like you can start with this linear regression. Okay, linear regression you can start, you can open this, and you can see how the coding is done for linear regression. Then you can see how the coding is done for logistic regression, etc. I have worked hard in these 2 days, and I have made all this for you guys, so that you can understand the coding better. Okay, because coding might not come in the exam, but it is important that you know how to code also, right? Because you are learning machine learning. So definitely somebody might have asked you how to code this. So you just need to have your data, and you can fit in this code, and you can see your results. Okay, is it clear?
Yes, sir. Thank you.
Okay. Okay. So let's again return to wherever we are, that is our slides. Yeah, so is my slide visible to all of you?
Yes.
Yes, right? Okay, so let's go and discuss some of the questions. Okay, so question number 1, is it visible, guys? Hello?
Yes, visible.
Yeah, visible, right?
Yes, sir.
Yeah. So which of the following is estimated by the expectation maximization EM algorithm for this Gaussian mixture model GMM? K, number of components, pi k, mixing coefficient of each component, mu k, that is mean vector of each component, and sigma k, that is covariance matrix for each component, and E, none of the above. So any guesses for this?
Sir, B, mixing coefficients.
B, C, D, sir.
B, C, and D.
Yeah, absolutely right. B, C, and D, right? Yeah, absolutely right. B, C, and D. A, we have to predetermine it. Okay, K is the number of components, but this we have to predetermine. Okay, that is not estimated by our this EM. Okay, these 3 things are estimated by our EM, that is mixing coefficient, mean, and covariance. So B is right, C is right, and D is right. Okay, so B, C, and D is the correct answer. Okay, number of components Gaussian cluster need to be predetermined. Okay, so this K, this needs to be predetermined. This is not estimated, but it is already predetermined. So the EM algorithm estimates the all the 3 things: mixing coefficient, mean, and covariance matrix. Okay, so is this clear to all of you? I think it is clear. Okay, so let's move on to the next question. Which of the following is true about the responsibility term in GMM? Assume standard notation used in the lecture. Okay, so whatever has been used in the lecture, this notation has been used there. Okay, so can you guess what is the right answer? this n is the number of data points, k means cluster. Okay, this n means number of data points, or k is the cluster. Okay, so that is how what is the correct answer? Can you guess, guys? Okay.
A, sir.
A is okay. A. Any other guesses?
D, sir. D.
D. Okay, D. Okay, so the right answer will be yeah, D is right. Yeah, absolutely, D is right. And another thing, what is right is B. Okay, why D is right? Because this is a probability. Okay, any point for any cluster, this is a probability, nothing but probability. So the probability value is between 0 to 1. So that is why D is correct. And why B is correct? Because whenever we are summing it for number of data points, okay, number of data points, that will be equal to 1. So B as well as sorry, A, oh sorry, cluster, sorry, yeah, cluster is right, sorry, cluster is right. So A as well as D is your right answer. That is whenever we will sum for each cluster, okay, so that will be right answer. So this is the responsibility term for each point, and whenever we are summing it for each cluster, that will be equal to 1 for all data points. And again, this is a probability term, so this probability term will be between 0 to 1. Okay, so A as well as D is the correct answer. Yeah, this is not the correct answer, because here we are summing for number of data points. Actually we have to sum for clusters. Okay, so we find this for a particular data points, and then we sum it for cluster, not the other one. That so first we will find the responsibility term for each data point, then we sum it for cluster, not the other way around, that we don't find responsibility term for a cluster and then sum it for a data point. That is not right. We first find responsibility term for each data point, and then we will sum it for cluster. So option A as well as option D is your correct answer. Okay, is it clear? Am I audible?
Yes,
Hello?
yes, sir.
Okay. So suppose we have a Gaussian mixture model of 3-dimensional data with 4 Gaussian, and we use a model with full covariance matrices. How many parameters are in the model? So any guesses for this? 3-dimensional data, that means we have 3 variables, okay, and we have 4 Gaussians. So how many number of parameters needed? Any guesses for this Gaussian mixture model? Okay, so let me ask you, for one Gaussian, how many parameters needed? So one parameter we need for mixing coefficient. Okay, because each Gaussian will have one mixing coefficient. Okay, so our pi will take one value. Now what about mu? Mu will take number of values. Mu will take number of values as dimension. Whatever the dimension is, so mu will take that much value. So 1 for mixing coefficient, and d for d is the number of dimensions. So d is the d for our mean. Now what about covariance? Covariance will take d into d plus 1 by 2. Okay, because one term will be common. As I have shown you, one term will be common. Okay, in covariance. So covariance will take d plus 1 by 2 values. So again I am telling, one value will go for each cluster. If I consider, one value will go for mixing coefficient, d value will go for d-dimensional data, and d into d plus 1 by 2 value will go for covariance. Okay, and if we have k cluster, so k into all this sum. Okay, so now we have 4 Gaussian, so k equals to 4 and d equals to 3. So our answer will be, for one, if I calculate for one cluster, if I calculate, so 1 will be for mixing coefficient, okay, and for three values will be for mean. Okay, one is for mixing coefficient, that is pi. Okay, 1 is for pi, 3 is for mu. Okay, and sigma will have 3 into 3 plus 1 by 2. Okay, sigma will be 3 into 3 plus 1 by 2, that is 3 into 4 by 2. 4 by.
So how is it 3 into 3 plus 1 by 2? Can you just tell that again?
Yeah, covariance, whenever we are taking covariance, so covariance is the covariance of xi as with yi also. So like we have 3 data here, xi, yi, zi. So 3 here, 3 here. Okay, now this first will have values with this 2 as well as this 3. So that is how we write this. Okay, so if you will remember, like if how to explain you, to have the sum of 3 consecutive number, what we will do n into n plus 1 by 2. So something like this only, because you have d-dimensional data. Okay, covariance is between d into d cross matrix. Okay, d into d cross matrix. So it will have d into d plus 1 by 2 terms. So if you remember the code I have shown you, when I have shown you the covariance, here for two values were there, and two inputs were there, xi, yi. But for each cluster we have 4 covariance, and out of this 4 covariance, 2 points are same. So that is why 3 for that. Okay, so n into n plus 1, so there 2 into 2 plus 1 by 2. So that is why 3 values. Okay, should I show you the code again? Okay, let me see if I can show you.
Sir, please repeat, sir.
Yeah. So here what happens is, covariance when we are taking, it is of d cross d, means how many input it has, it will be forming cluster of it. Like 2 input we have, right? So d cross d means 2 cross 2 it will form. If we have 2 values, so 2 cross 2 matrix it will form. That means it will have 4 values. But out of this 4 values, 1 value will be common. This diagonal matrix is always common. So that is why we have 3 values. So like that. Okay. Okay.
Sir, this covariance matrix you tell me, sir, this one, summation.
Summation. Yeah. This is what I am telling you. Yeah, this is what I am telling you. You have to understand covariance first. Okay. So if you understand covariance, then only you can understood it well. Okay, so covariance is between, like if you have 2 data xi, yi, covariance is between 2 cross 2 matrix will form. So out of this 2 cross 2 matrix, 1 value will be common for this. So that is why we have 2 cross 2. Okay, 2 into 2 plus 1 by 2. So that is why we have 3 values. So here also we will have 3 values. So 3 into 3 plus 1 by 2. So that is why you will have 3 into 4 by 2. That is why you will have 6 values. Okay. You just go through the covariance thing. So once you will go through the covariance, what is covariance, how covariance of 2 variable is computed, then you can got this. Okay.
Okay.
Actually, in the diagonal of the covariance matrix will be equal, right, Nasser?
Yeah. That is what I am telling.
The
That is
diagonal of the covariance matrix will
We
be
have seen in the code also, right? Whenever I was discussing the covariance matrix, the diagonal was equal, right? So that is why 1 value will be less.
Diagonal of the covariance matrix is equal. That is why we are taking this as 3. That is d into d plus 1 by 2.
Yes.
D is the dimension.
Yes. Absolutely. So by this, for one cluster, you will have 1 plus 3 4 into 3 plus 3 into 4 by 2. That is 6. So that means for each cluster you will have 10 parameters. Okay, for each cluster you will have 10 parameter. 1 for pi, 3 for this mu, and this is a covariance matrix. So that is why 3 cross 3. That you will
Screen
have.
is not visible.
Screen is not visible. Okay.
Yeah, now it's visible.
Yeah, visible, right? Okay. So yeah,
Yes,
1 value for mixing coefficient, that is clear, right? 3 value for mu, that is also clear. Now covariance is a matrix. Okay, so 3 cross 3 matrix when we will take, 3 cross 3 matrix means how many elements? 9 elements, right? 9 elements, but 3 elements will be common. Okay, so that is why 6 elements. Okay, so that is why 3 into 4 by 2. That is, this is a formula you can learn. Otherwise, you can see by you can visualize it. So 3 value will be common. So that is why 3 into 4 by 2. So that is 3 into 4 by 2 is 6. So 1 plus 3 plus 6, that is 10. So 10 parameters for each cluster. And how many cluster we have? We have 4 clusters, right? 4 Gaussians. So 4 into 10, that is 40. So 40 will be your answer. Okay. So is this clear? Yeah, covariance
The
you
green
can.
is not visible, sir.
Is it visible to all of you or not visible?
Just,
Visible
no,
for
sir.
me.
Just now it's went, sir.
Yeah, visible, right? Yeah, visible. Yeah. Okay. So yeah, so one value for pi, 3 value for mean, and covariance will be d into d plus 1 by 2. So that is why here we have 3-dimensional data. So that is why 6. So 1 plus 3 plus 6 equals to 10 for each Gaussian, and we have 4 Gaussians, so 40 parameters. So B will be your correct answer. So it is clear for pi. I think it is very
Sir,
clear for.
suppose,
Yeah, please.
sir,
Yeah, please.
sir,
Am I
suppose
audible?
if we have 4-dimensional data,
4-dimensional data. So one value for one value. Yeah, let's say 4-dimensional data. So one value for pi, right? Pi will have only one value. That is
pi.
clear, right? One cluster, one
Yes,
value.
sir.
Yeah. Mean will
Yes.
have 4 values, right? Because 4 xi,
Mu will
yi,
be
zi,
4.
ai, something like that. So 4 dimensions. So that is why 4 value for mean. Clear, right? Clear or not? Hello?
Yes, sir.
Yeah. And then covariance will be 4
Your
into.
voice is breaking, sir.
Is it breaking for everyone or not?
Sir, even screen is also not coming, sir. Just now it's fine, sir.
So for me also it is breaking, sir.
It's
your voice.
network issue, I think, sir. Your voice is not audible. It's breaking. And even that screen is also not visible, sir. Just now it's fine.
Yeah, it might be network issue because I am at home. Okay, so is it
Yeah,
visible?
sir.
Is it visible?
No, sir. Screen is not visible. Yes, sir. Yes, sir.
Visible, right? So 1 plus 4 plus
Yes.
1 is clear, right? 1 for
Yes, sir.
1 for this number
Yes,
of
sir.
parameters, 4 for
5.
4 for mu,
Yes.
that is mean, and for covariance 4 into 4
Yes.
plus 1 by 2. Okay, 4 plus 1 by 2, that will be
Yes,
equal
sir.
to 5
Yes.
into 2. 5 into 2, that means
Yes,
that
sir.
will be equal to 10. Okay, so 10 plus 5 10 plus 5 is 15. Okay, so 15 for each cluster, and then we have 4 Gaussians, so that will be equal to 60 if we have 4 dimension data. Okay, clear, right? Hello?
Yes, sir.
Yeah, clear, right?
Yeah, yes, sir. Yes, sir. Yes, sir.
Yeah. So that is
Yes,
how we will
yes.
solve this. Okay, now let me move on to the next question. Okay.
The pi will be 1 for any dimensional data, is it, sir?
Yeah. Pi is according to cluster. One cluster means 1 pi, because pi is the mixing coefficient for each cluster,
Okay, sir.
right? So one cluster means 1 pi. Okay.
Here they haven't mentioned how many clusters.
Here I have mentioned, right? 4 clusters are there.
Okay,
Four,
okay.
4 Gaussians are there, right?
Okay, sir. Okay.
Oh.
Nice. Thanks.
Yeah, now select the correct statement about the EM algorithm for GMM. In the mth iteration, the gamma value are computed using parameter estimate computed in the same iteration. Okay, in the mth iteration, the gamma values are computed using parameter estimated computed in the m minus 1th iteration. C is the sigma k parameter estimate are computed during the E step, the mu k parameter estimated during the M step. So any guesses for this? Yeah, any guesses for this, guys?
Sir, B.
Sir,
Yeah,
B, I think.
B and D. B and D, right? Yeah,
No, just B.
just D. Just D or B and D?
No. D also, yeah. D also.
B also, right? Yeah.
B and D, sir.
Yeah, so B and D are the correct answer because this mu k sigma k that will be estimated during the m step. Okay, each step we are only assuming the parameters, but whatever we are doing in the m step, updating the parameter in the m step. Also, this gamma k it is computed using parameter estimate computed in the m minus 1th iterations. Okay, so whatever the parameter has been estimated in the previous iteration, then only we will calculate this gamma k. So B as well as D is the correct answer. Okay. Okay. So this is, I think, theoretical question. No need to discuss. So what does soft clustering means in GMM? There may be samples that are outside of any cluster boundaries. The updates during maximum likelihood are taken in small step to guarantee convergence. It restricts the underlying distribution to be Gaussian, and the samples are assigned probabilities belonging to a cluster. So any guesses for this?
Sir, B and D.
B and D. Can you write in the chat box? It will be more easier for me. Yeah, D samples are assigned probability belonging to the cluster. Yeah, and anything else? Yeah, so D is the correct answer, right? Absolutely, because this GMM is a type of soft clustering. So instead of assigning each data point into a separate cluster, a probability or likelihood of that point belonging to the cluster is evaluated. So option D is the correct answer. Okay. Okay, so let's move on to the next question. So this is the question. Okay, for a set of points given in orange, okay, these are the set of points that is given in the orange. The density estimation of a GMM is given below. What is the problem evident in the image? Okay, this is nothing but your clusters form. Okay, or this is nothing but your probability distribution. So pi i's are too big. Okay, that is first problem. Is it so? Or the B, the cluster are not sampled from a Gaussian distribution. This can be a problem. K is small, okay, or there is no problem. So any guesses for this? What is the problem evident for this image when we are doing this Gaussian distribution thing? Yeah, yeah, B is right. Any other guesses? B is right, yeah, true, because this is not a Gaussian distribution, so that is why that is a problem. Yeah, B is very right, that is true. Anything? Yeah, C is also right. K is K is large actually. Okay, K is large here. If K is K is small here. If K is large, K is the number of cluster. If say K is only 2 here, but if I say K is 100, so I can fit 100 Gaussian distribution like this. Okay, like small Gaussian like this. I can fit small distribution like this. Okay. Yeah, I can fit I can fit small distribution like this. Okay. Okay, like that. So that is how this is a problem. B is, you all have guessed right, because this clusters are not sampled from Gaussian distribution. But if we make a large number of cluster, that is K is small here, but if we increase the value of K, so we can fit Gaussian distribution with this data also. So B as well as C is your correct answer. Okay, so is it clear how C is right? Is it clear to all of you?
Yes, sir.
Okay. Now next question, for the GMM model, what is the value of K? 1, 2, 3, 4, 5 or 6? Any guesses?
4.
Yeah, 4. Any other guesses? Yeah, absolutely right. As GMM is a soft clustering, so you can't see the boundary. Okay, you have to see where is the distribution form. So one is this distribution is clearly seen, and the one this distribution can be seen, and the one this distribution can be seen, and another one this distribution can be seen. So there are four different distribution: 1, 2, 3, and 4. So the value of k is 4. Okay. GMM is a soft clustering, so you can't go by boundary. Okay, this clusters are overlapping, but still these are separate cluster, because seeing the Gaussian distribution, you can understand that these are separate clusters. Okay, is it clear?
Yes.
Yes.
Okay. Now question number 8, the expectation maximization. Yeah, we have two statements, statement A and statement B. Statement A, by the expectation maximization algorithm is used to find maximum likelihood estimate for model parameter when data is incomplete, missing, or contain hidden variable. Statement B, the EM algorithm uses random value for missing data points and iteratively update this value until they stabilize. Which of the following is true? Option A, both statement A and B are true. Option B, both statement A and B are false. Option C, statement A is true, B is false. And option D, statement A is false, B is true. So any guesses? Yeah, D, someone is telling D.
Option A is the
Yeah, A is, yeah. So yeah, A is true because both the statement are true. We have just discussed the expectation maximization algorithm is used to find maximum likelihood estimate for model parameter when this data is incomplete, missing, or contain hidden variables. And statement 2 is also true. The EM algorithm uses the random value for missing points and then iteratively update these values until they stabilizes. Okay, so statement A as well as statement B both are true. Okay, so option
Yes.
A is correct. Okay, option A is correct. Now suppose we are again, this is number of parameters type of thing. Yeah, suppose we are trying to model a p-dimensional Gaussian distribution. What is the actual number of independent parameters that needs to be estimated? So here we have p dimension. Okay, so how many parameter will be there for each Gaussian distribution? Okay, now we are talking about only one Gaussian distribution. We are not talking here about the Gaussian mixture model. We are just talking about a single Gaussian distribution. So how many independent parameter will be there? Any guesses? So we for single Gaussian distribution we have two things. One is sigma, one is sigma, and there is mu. Okay, these two are there. Or you can say one is sigma square or this capital sigma, and one is mu. So mu will take p data, and this capital sigma will take p into p plus 1 by 2. That means p plus p into p plus 1 by 2. That will be equal to this p plus 3 by 2 when you will solve this. So option F will be your correct answer. Okay, is it clear?
Yes, sir.
Clear, right? Because this is for mu, this is for mu, and this is for sigma or sigma square, you can say. Yes, take it capital.
So pi will be 1, or
No, here it is
so
only
plus
for
1 will not come, right?
here it is only for Gaussian distribution. It is not for Gaussian mixture model. Whenever Gaussian mixture model is told, then you have to take one value for pi also. But here it is only for a Gaussian distribution. So there is no account for pi here. Okay, so one is mu and another one is sigma. Complete. Okay.
Okay.
Okay. Okay, so just you have to add p plus p into p plus 1 by 2. You take the LCM and you will be factorize this, and you will be having this. So F is your correct answer. F is your correct answer. D is written here. F will be your correct answer. Okay.
Yes.
Okay. Now we are with the last question. Okay, this is again a visualization type of question, so but this is also an important question. So if in each of the option the diagram contains a log likelihood function for a particular problem as well as initial value of the parameter used in execution of EM algorithm. In which of this given scenario will the EM algorithm be able to achieve global maximum? So in each of this expectation maximization, what we are doing is we want to find the maximum log likelihood. We have to find parameters such that our log likelihood will be maximum. Okay, so we have to check in which graph we can reach the maximum log likelihood. Okay, so here if you check the A graph, what the problem here is, yeah, we will be reaching the maximum likelihood, but this is not the global maximum, this is the local maximum. After giving to the local maximum, our algorithm may not know, because after here the likelihood decreases. So our algorithm, after reaching here, it will say this is the maximum, but actually the global maximum is here, so our algorithm fails here. So option A is not the correct answer. Okay, now what about this? Yeah, our initially we are here. Now either we can go left side or we can go right side. So if we will go left side, there is no point in going left side because we can't find the maximum. But if we go to the right side, yeah, we will reach a maximum, but this maximum will not be the global maximum. This is a local maximum. Okay, this is a local maximum, L. Okay, but if we need to go to the global maximum, our algorithm will fail. Now what about here? Here also, if we move to the left side, we will find the maximum, but this maximum will be a local maximum. Okay, this maximum will be a local maximum, and this this maximum will be a global maximum. Okay, but the problem is if we go this side, then we will have a local maximum. So this is a problem with this. So this also we will eliminate. Why we are eliminating this? Because one side if we will move, we will stuck in a local maximum, and our algorithm will say this is the maximum, but actually the global maximum is over here. So again this we will eliminate. Now what about this here? In this question you will say this is not a maximum. This is kind of, yeah, this is a global maximum as well as local maximum. So if we will go there, we will reach our global maximum. So option C is right according to me. What about option D? Option D, here see, this is a local maximum. Okay, this is a local maximum. I am marking this. This is a local maximum. So again, if we will go here, our algorithm will be here only. Our algorithm will reach the global maximum, but here also it will stuck a local maximum. Okay, so option C is our correct answer. Okay.
So, but how do we know where that theta is lying? It can be on any point, right? It can be a random.
Yeah, it is random, right? But here in this question, the theta is here. Okay, here in the question, the theta is here.
Okay.
Here the theta is here. Here the theta is here. Okay.
In D diagram, it is slightly going down, is it, from the local maximum? The D, sir.
D here this is a,
slightly
yeah,
going
this
down.
is a local maximum, but it is slightly then again decreasing, right? So that is why this is a local maximum, not a global maximum. Okay.
Here it is keep on raising it, and then after the global
Yeah.
maximum,
Here only it will keep on raising. It will go to the global maximum first. Okay.
Okay.
So option C is the correct answer. Okay. So by this I am
So can I ask one more doubt in our previous class, if you don't mind?
yeah, please.
What is the difference between the
Single link clustering and complete link clustering, right? Okay, so that question I can cover in an extra session that I will take on probably 18. Okay, so there I can clear your doubt. Okay, single link clustering, and but question you have to do with single link clustering only. Okay, you have to find if you have to find the minimum distance or maximum similarity.
maximum similarity? Okay.
Yeah, and we have to cluster hierarchical clustering. So you have to cluster 2 points at a time or 2 cluster at a time. You have to see those points must have smallest Euclidean distance or maximum similarity. Okay.
Because I don't know the difference between the single linking clustering and then complete linking.
Yeah, okay.
As of now, we know the single link clustering.
Okay,
the minimum
okay,
distance and the maximum
yeah,
similarity.
okay. I will keep a slide on that single link and that complete link clustering. Okay, in the
Sure.
extra session
Thanks.
after that next week. Okay, not next week, but after next week. Okay. Okay. Doubt
Okay,
regarding
thanks.
exam, is there any negative marking? This is the first time I am reading. Actually, I am a TA, okay, so I don't prepare the exam paper. So anyone of your friend who has taken the NPTEL before, they can answer it well, okay. So yeah, there will be a negative marking, that is for sure. Otherwise, you will just guess randomly. So there will be a negative marking, okay. Am I audible? Hello.
It's getting broken, sir.
Am I audible now? Hello? Am I audible? Hello, am I audible? Okay, let me write.
No.
Am I audible? Hello? Okay, let me write in chat. Okay, we have completed the session.
Yeah. Now it's audible.
Now audible, right? So yeah, so TA, I am just a TA of this course. I am not preparing the question paper, so I don't know what question will come or not, but definitely there will be negative marking, otherwise you will just randomly guess all the questions and that is not the point of taking the exam, right? So definitely there will be negative marking. You can ask any of your friend who has taken the course previously, they can guide you well, like what will be the question paper pattern, etc. They can guide you well. Also, I think you will get mails from NPTEL support team regarding this, when will be your exam and how your exam will be taken, okay. Hello.
Sir, extra sessions.
Yeah, extra session, only one extra session I will take on 18, I think, okay.
Okay.
Okay, so bye with this.
Thank you, sir. Thanks.
Okay.